Hi everyone, my name is Rahul and I will be presenting our paper titled Compatibility Aware Heterogeneous Visual Search. Visual search is a general problem with many applications. In this paper, we consider three: fashion retrieval as shown on the left, face retrieval shown in the middle, face verification shown on the right. A typical visual search pipeline is as follows. Given a gallery database of images, we use an embedding model phi to project these into an embedding space. So the 7 gallery images are mapped to the points G1 through G7. When a query arises, we use the same embedding model phi to project it into the embedding space as shown by the point Q. Finally, the closest match to Q is found through a nearest neighbor search, which in this case returns the image of the same person as the query. As you may have noticed, we use the same embedding model for both the query and gallery images. This causes several issues. Typically, the gallery database is housed on a cloud server, whereas the query arises from an edge device. This means that the size of the embedding model is constrained by the compute constraints available on the edge device. Choosing a small embedding model often leads to a large loss in accuracy. To overcome this drawback, we propose a heterogeneous visual search system that decouples the query and gallery embedding models. But as you may have noted, the two models project the query and gallery images to two different embedding spaces. The key to building a successful heterogeneous visual search system lies in ensuring that the two embedding spaces are compatible. We formalize this notion of compatibility through the compatibility criterion. Given two models phi-q and phi-g such that phi-q is smaller than phi-g, we require the following inequality to hold. Here M is a retrieval metric such as the top k. On the two extremes, we have homogeneous visual search systems with either the query or the gallery models on both the client and the server. In the middle, we have our desired heterogeneous system. In the paper, we look at two ways of achieving compatibility. First is by optimizing the query model's weights, which we show can be achieved by minimizing the recently proposed BCT loss. Second is by optimizing the query model's architecture, for which we propose the CMP-NAS strategy. We briefly look at the CMP-NAS method for obtaining the most compatible query model. Essentially, CMP-NAS is a three-step method with the first step involving training the gallery model. We do this by minimizing the cross entropy between the network's prediction A and the label B. The second step involves training a query supernetwork. This supernet encodes different architectures as paths in the graph. To train the supernetwork, we first uniformly sample an architecture or path denoted by A and shown in red in the figure on the left. Given A, we minimize the BCT loss for this architecture. We repeat the sampling and loss minimization step multiple times to obtain a trained query supernetwork. Finally, using the trained supernetwork, we find the most compatible query architecture by maximizing a reward R. We consider different rewards in the paper and solve this maximization using an evolutionary algorithm. We look at some key results on the face retrieval task. The y-axis here represents the retrieval metric. The lower bound of performance is achieved by a homogeneous system containing a MobileNet v2 model on both ends. This system achieves 77.1% accuracy while consuming 329 megaflops. At the other end, the upper bound of performance is achieved by a homogeneous system containing a ResNet 101 model on both the ends. This system achieves 86.7% accuracy while consuming 7597 megaflops. The ideal performance of a heterogeneous system must lie between these two. When we only consider the weight compatibility, a heterogeneous system containing a MobileNet v2 and ResNet 101 obtains 81.2% retrieval accuracy with a cost of 329 megaflops. However, when we optimize the query architecture using CMP-NAS, our heterogeneous system achieves 85.1% accuracy with a comparable cost of 327 megaflops. We compare the performance against many recent state-of-the-art architectures and find CMP-NAS, shown in blue, outperforms all of them. Lastly, the models searched by CMP-NAS using different methods and shown in blue outperform the ones searched by vanilla NAS algorithm shown in yellow. We thank and welcome you to join us for further discussions in the poster session.